Yeah, good day and welcome back. Let's continue. In structures, when we join the materials, we can join them in maybe two different manners or more. But for ourselves, we're going to focus on two manners, which is series arrangement and parallel arrangement. So we're going to have this series arrangement and parallel arrangement. So series arrangement is when we have a certain component uh, joined end to end like this. This is the end of this, then this is also the end of this, just like that. We call it end to end. So we join the material end to end. Therefore, what you have to know is that if you take this component and then you apply a force like this, let's say you apply the force of 10 Newton. So what's going to happen here is that this component, let's say component number one, this is component number two, this is component number three. So these three components, they're going to get stretched with the same magnitude, which is 10 Newton. So once you apply force of 10 Newton, this material or this this part here will be stretched with a magnitude of 10 Newton. So even this part here will be stretched with magnitude of 10 Newton. So even this one will be stretched with the magnitude of 10 Newton. So that's why we're going to say that this force, you can say it's the total force or is the applied force. So this force, which is the applied force, will be equals to the same, will be equals to the force in this section number one. And then the very same force that will apply here will be the very same force that will be experienced here on section number two. The very same force that will apply there is the very same force that will be transferred to this component number three. So we say that the force is the same or the force is common. So that is one of the conditions for series arrangement. If your structure or your support it's having three or more components arranged in this manner, then you must know that the force will be the same throughout. Right, so the extension, okay, when you pull this thing, maybe you've attached this end on the wall or you fixed it or somewhere else. So what's going to happen is that when you pull this side, if you attach this thing on the wall will react and pull in opposite direction. So, but the wall will react with the same magnitude but in opposite direction. So it will also pull with the force of 10 Newton. Right, so as you pull this thing, you stretch this thing, I can say maybe obviously the length of this thing is going to increase due to that pull. So if this material is elastic, can stretch, is stretchable, then we expect the length of this to increase as well. So this will find that this thick one is going to increase. The length of this is going to grow from here to there. So this length will be increased due to this force of 10 Newton. Remember, when you apply force of 10 Newton here, even this member is going to experience the force of 10 Newton. So this thing is going to stretch from here to there due to that force. So even this component here is going to stretch from here to there due to that force. So even this one is going to stretch. So this one here, we're going to call it X1. This part from here to there, it's X1. Then from here to there is X2. From here to there is X3. So here, the extension is not going to be the same. Yes, these sections are going to experience the same force, but this length that we see here, which is the X or the extension, this length here, it won't be the same as this length. Why? Because we are going to calculate the change in length for x using this formula. X will be equals to F L over A E. So this one is just the force, we know it. This one is the length. The length, we know the length. This one is the area. This one is modulus of elasticity. So this one depends on the material. So actually this one is telling us maybe about the stiffness of the material, or how easy the material it is to stretch. When it comes to stretching, is it gonna be stretched easily, or is it gonna be stretched by applying small force, or is it gonna be stretched by applying the bigger force? So this thing is telling us about that, or this material, does it stretch easily, or it need the bigger force to stretch it. So like a rubber band, when you take a rubber band and stretch it, it will just stretch without more resistance. So you can stretch it with less force. So we say that rubber band is going to have the smaller value of E. But if you take the steel or maybe the wood and then you try to pull it, the length is going to extend, but you might not even recognize that. With your naked eye, you might say that it's not stretching at all. So it's going to stretch, but it's going to stretch with a very, very small magnitude. So it means that it's not easy to stretch it. So it means that if the material doesn't stretch easily, it means that that material will have the bigger value of E. So this E is called the modulus of elasticity. So this is the area. We know the area, don't have to explore more. So this extension will depend on the area, meaning that the smaller the area, as you can see, this x and this, they are inversely proportional. The smaller the area, the bigger the extension. So that's why you see this length here, from here to there, this extension here, it's longer. It has to be longer compared to the rest. So why? Because this part is having the small cross-sectional area. So the part that have small cross-sectional area will stretch with the bigger length. This one with the bigger area, this part is having the bigger area. The bigger the area, the smaller the extension. So this thing will extend a bit. So if you want to know the total extension of this thing before we apply force, we can say that this is the original length. So if you want to know the total extension or total length, you have to take this part, this extension here, plus this extension here, plus that extension. So those three extensions, which is this part, will give you the total extension. And if you want to know the final length, then you will take this original length here plus this total extension. Right, so we say that the maximum stress, and note this one please, maximum stress occurs at the smallest cross-sectional area. So like for an example, if we pull this thing at a certain magnitude, this thing is going to have the bigger stress. Okay, let me write the formula for stress. Stress is force over area. So yes, in this arrangement, we have the same force, but we've got different areas. So as you can see, stress is inversely proportional to the area, meaning that the smaller the area, the bigger the stress, or the bigger the area, the smaller the stress, meaning that here, where you have the smallest area or the smaller area, that's why we're going to have the bigger stress here. Then where you have the big area, That's why we're going to have the minimum stress or the smaller stress. Therefore, the maximum stress, which is the biggest stress, we're going to find the maximum stress or biggest stress where? At the smallest cross-sectional area. If you want to achieve maximum stress, you have to apply small, you have to use the small area or minimum area. Right, so if it happens that the question says that the maximum stress is 10 MPa, don't say the stress in here will be 10, the stress here will be 10, the stress here will be 10. We won't have the same stresses here since we have different areas. So when they say the maximum stress is 100 MPa, it means that that's maximum stress. That stress is the stress for here. It's the stress for that part where you'll have the smaller area. Then if they say the maximum stress is 20, sorry, if they say minimum stress is 20 MPa, it means that that minimum stress will be the stress for this portion. So you'll find the minimum stress at the biggest cross-sectional area. So it will be the vice versa of this. Minimum stress, you'll get minimum stress at the biggest cross-sectional area. Right, I'll try to save time because I don't want this video to last long. The same thing, I won't do the calculations. I will just give you approach and give you the basic knowledge about these things. You'll do the calculations since we have the solutions for this. Okay, parallel arrangement, we already met parallel arrangement from the previous lesson. We had something like this. Maybe we have two ropes like this, two ropes, and then from these two ropes we hang, I don't know, maybe we hang a chair here, meaning you are trying to pick up a chair, and then that chair, you want your friend to help you to lift this chair. So you put the rope there, you put the rope there. So as you can see, this rope, it's parallel to this. So what you have to know in parallel, we have to know that the load of this thing will be shared. So if the load of this thing is 10 Newton, the load of this chair is 10 Newton. Then it means that someone who will be on this will carry 5 Newton, and then someone on this side will carry 5 Newton. So the weight will be shared among the supporting structure. It's unlike here. So here, if you hang a chair of 10 Newton, this member is going to carry that 10 Newton, this one will carry 10 Newton, 10 Newton. But here, they will share the load. So we say that F total in this case, or you can say F applied, F total will be this. F total will be shared, or will be equals to F1 plus F2. So in this case, it's no longer like this. F1 is no longer equals to F2, or FA is no longer equals to F1 and blah, blah, blah. Yes, in this scenario, F1 will be equals to F2, but the fact remains that these two will share the load. But this one will only, this force, this thing will only carry the same magnitude under two conditions. Only if this chair is placed exactly at the center of this, and only if this material is the same as this material. So if this material and this material of these two rods, if the material of these two rods are the same, and then the chair is placed in between, exactly in between, then yes, this support will carry 5 half, this one will carry half 5. So sometimes you'll find that the chair is not placed at the center, or these ropes are made from different materials. So if that is the case, you'll find that if the chair is weighing 10 Newton, then we'll find that this rod will carry 7 out of this 10, and then this other rod will carry 3. So in this case, they will share this load at 10, but they are not going to handle the same magnitude. So one support will carry more load, the other one will carry less. So that's what we have to know with this parallel arrangement. And then again with parallel arrangement, we say that the extension. So obviously, if we put the load on this rod, we expect this rod to grow. The length of this rod will grow from this size, maybe to this size, from this size to this size. So once this rod grows, remember original this thing started there and ended there, the length, original length. This is the original length from here to this LO. So once you hand the load, that load is going to pull this rod downward. So this rod will end up stretching. So that length now will grow from this size to this size. So finally the length will grow from this size to this size. So this part that you see is the one that we're going to call it the change in length, which is x. So this is the formula to calculate x. So in this case, for parallel, we say that the change in length of this member will be equal to the change in length of this member. So meaning that if this one support extend with 2 millimeter, this one will extend with the same magnitude, 2 millimeter as well. Therefore, we say that x1 equals to x2. Right. So now let's check an example quickly. Right. Let's check this problem here. Number 3. Yeah, this is the problem that I want us to check now. A round steel bar 5 meter in length is subjected to a tensile load of 10 kN. The bar has a diameter of 40 millimeter over a length of 1.5. Okay, let me try to draw it. Yeah, just to be quick, let me take this route. Okay, let me read the question quickly. Around the yeah, right. Yeah, according to that statement, we're going to have something like this. They're saying that this thing is having the total length of 5 meter. And is subjected to a tensile load of 110. So we're going to apply a tensile force of 110. Smooth on here. The bar is a diameter of 40 millimeter over a length of 1.5. So for the first 1.5, which is this one here, from here to there, this thing is going to have a diameter of 40 for a length of 1.5. So diameter is going to be 40. A diameter of 32 millimeter over a length of 2 meter. So for the next 2 meter from here, which will be from here to there, 2 meter. The diameter of this portion will be 32. And the 19 millimeter over the remaining length. So this remaining part here, this part is going to have diameter of 19. Then they didn't give us the length. They don't have to give us the length. You can find this length here for this portion by saying 5, which is total length. 5 minus 1.5 minus 2 will give you this remaining length. So this plus this is 3.5. Then it means from here to there will be 1.5. Right. So what are we looking for here? Calculate the total extension. So to calculate the total extension, we're going to use this formula now. This one, this thing is the same thing as this. So we're going to use this formula. So total extension will be equals to x1 plus x2 plus x3 plus x4. Oh, sorry. Okay, this thing depends on the number of sections that we have. You see x total equals to x1 plus x2 plus x3 is because we have 3 sections. We've got 1, 2, 3. So if it happens that the question have another section, like we put something here, which is going to be the fourth one, then you have to put x1 plus x2 plus x3 plus x4. So this x what depends on the number of sections that we have in that particular problem. So to calculate x total, to calculate that x total, we're going to say just copy that formula xt equals to x1 plus x2 plus x3. So let me go back to the question, calculate total extension. All right. So x1 will be equals to f1 L1 over area 1 E1 plus a very similar same formula yeah, for x. Right. So the force that we are going to use here is going to be 110. So remember we said that in series force is common, meaning that F1 is 110, F2 is 110, F3 is 110. So we'll replace all these forces by this much. L1 is, let's say this one is number 1, this one is number 2, this one is number 3. So L1 is the length of this portion number 1, which is from here to there. So L1 is 1.5. You replace that L1 by 1.5. Area 1 will be the area of this section 1. So to calculate the area of this section 1, area 1 will be pi d squared over 4. So area 1 will be pi. Diameter, you change it to meters. 40 divided by 1000, from millimeter to meters, we divide by 1000, then we'll have 0.04. You square it. Then you get area 1. Yeah, so this will be area 1, and then E is the modulus of elasticity. So as I've said, E, let me see here if I can get what they're talking about E. But I've already spoke about E before, modulus of elasticity. Okay, anyways, elasticity here is the property of material to return to its original form when the force causing the strain is removed. Like when you take the rubber band and then you apply force on it, it's going to stretch. But once you release that force or remove that force, that rubber band will go back to the original shape or form. Therefore, if the material can do that, we say that kind of material we say that material is elastic. So Young modulus, which is that E, it's here. Young modulus is a measure of how easily a material stretches. Good. So it is this E, right? So now E is it depends on the type of material. So here we've used the same material. If we have the same material throughout, meaning if we have steel here and steel here and steel here, means that this E and this E and this E will be the same. So sometimes they might not tell you, or we have the same material, but if they then don't tell you, if from the question they just give you one value of E, if they just give you one value of E, then you must know that you have one material. If they give you two values of E, then we have two types of material. So like here, they only give us one value of E. So if they give us one value of E, then it means that we're going to have only one material. So if we have one material throughout, those E's will be the same. Okay, you replace this E with the value that will be given. In this case, E will be equals to 190 GPa. You replace this G. You will say 190 times 10 to the power 9. This is giga. So giga equals to 10 to the power not minus 10 to the power 9. So just be careful there. When you come to substitute here at E, you will say 190 times 10 to the power 9. So all this is right. E2, I'm not going to do it, but E2 you will follow the same thing. You will follow the same thing here. You'll just replace this thing by 2. And then you will come back again here and replace this diameter by 32. Remember, diameter for 2 is 32. Then you replace this by 32, 0.032. Then you calculate the area. That area will give you area 2. Then you are going to use that area here. Then you come again and calculate area 3. You use the very same formula. You replace this subscript here. You replace it by 3. Then the diameter for portion 3 is 19. So we're going to replace this thing by 19, 0.019. You get the area. So the area that you get there is the one that you are going to use here. Here. The area that you are going to use here. Then from there you have everything, and then you calculate total extension. So to calculate total extension, we just have to substitute here with all those values that we've discussed. Then the length for portion 2 is 2. We are going to replace this length by 2. The length for number 3 is 1.5. And that's how you'll calculate the total extension. Yeah, these two problems, this one and this one, I've discussed this one on the previous lesson. I'm not really going to repeat it, but this one is that part where the area, your area, to calculate your area there, you are going to use this. I've used what in the morning? I've used width minus d multiplied by thickness. So is this part, if you have a cross-sectional area like this, if you want to know the area, this thin part, the area of this part that I've just sectioned, excluding this is what you must use. So this W represents the length from here to there, diameter represents the length from here to there, the thickness represents the length from here to there. So from one of those questions, they're looking for, I don't remember, they're looking for this or this. Yeah, they're looking for width, W. So you have force, you have stress. You can calculate W there. So you have stress, which is force over area. So you are going to replace stress by that value, that given value, force by 180. Then instead of area, we are going to write this. Hopefully you have thickness, you have diameter. So the only thing that we don't have the width. Yeah, so due to time, I'm not going to do them. With this one, I'm going to do it here. With this one in number 5, with number 5, you are going to use this formula. X equals to F L over A E. So you see they give us this. You see this value here is the value for X. So X, it can be, they can call it the stretch. They can say this X is the stretch, or is the change in length, or is the elongation. Or they can say a length increases by. If they say a length increases by 2 millimeters, it means that 2 millimeters is the change in length. So if they say the length stretches by 0.25, so it means that 0.25 is X. So you have X is 0.25, but make sure you use the meters. Divide this thing by 1000. Then when you come to replace here, it must be in meters. They gave you the area there. That area as well, you must change it to meters. Then from millimeter squared to meter squared, you will multiply by 10 to the power minus 6. So remember this, it's very important as well. So if they give you a value like this, which is millimeter squared, to change this to meter squared, you just have to take this 2.238 multiplied by 10 to the power minus 6. Then in that way, you converted millimeter squared to meter squared. Okay, you have the area now. E, yeah, modulus, it's given. You replace it with it here. The length is 308, but change it to meters, so you divide by 1000. Then the only thing that we don't have is force, which is what they're looking for. They're looking for force, which is this. So we have everything except the force there. Yeah, this one you'll try it, but when it comes here, you will still use that area that I've just discussed. W minus E multiplied by T. This is the area through that hole, so we're going to use that. So this represents diameter of the hole. So if you cut whatever in through the hole, this is the cross-sectional area that you're going to have. Right. Yeah, let's check this one. Let's check this. A steel bar as shown on this sketch is axially loaded. So the word axial, it means that parallel to the length. So this is the length. So this force is applied parallel to the length. Okay, this thing is loaded axially. Then this force is going to cause the stress, maximum stress of 160 in the bar. Calculate the tensile force, the magnitude of this force. So now the solution will rely on this, depend on this statement. So if you still remember very well, I said that if they give you the maximum stress, it means that that maximum stress is the stress for this portion that will have small area. We said that maximum stress occurs at the smallest cross-sectional area. So that maximum stress equals to force over area. The area will be the smallest. So now when you calculate the force, you just have to make force the subject of the formula from this, which is going to be maximum stress multiplied by the area. So now the question goes between this area and this one, which one are we going to use? We are going to use the small area. Why? Because maximum stress occurs at the smallest area. So therefore, we are going to use this area here. This one at 30. Don't say area this one plus this one here. No, we have to use one area, either this one or this one. So we use this one because we have maximum stress. So total change in length will be the same thing with that one that we've discussed. You will use this. X total will be equals to x1 plus x2, which is going to be FL over AE plus FL over AE. So that force that you will get here will apply to this and that, meaning that if you've got 10 Newton as your force here, if your answer is 10 Newton here, then it means that this portion will be stretched with the force of 10 Newton. Even this one will be stretched with the same force of 10 Newton. Remember, in series, force is common. Force will be the same in portion 1 and portion 2. So you'll use that force here, and which will be the same force. The length for this one will be 250. You will replace this L by 250 but change it to meters. The length for the second part is 180. Replace this L by 180. Area, use diameter of 50. Area, use diameter of 30. You have everything. Then modulus of elasticity is given as well. It's 250. Use 250, 250. Then you'll get the total extension. Right? For this kind of problems, let me stop there. Just remember the maximum stress occurs at the smallest cross-sectional area. Minimum stress occurs where you'll have the bigger area. So if the statement states that the minimum stress here, then that stress will be the stress for this portion. But if they say maximum, then it will be the stress for this portion. Right, thank you.